Well, welcome everyone. My name is Eric Makala from Cadmus Group, broadcasting out of Boise, Idaho, and I'm with my cohort Howard Wigg out of the Hawaii State Energy Office. I'd like to welcome you to our third webinar that we're putting on to introduce the 2015 IECC code to you. Excuse me. We've done two on residential so far. This will be our first one into the commercial provisions of the International Energy Conservation Code with Hawaii amendments. And I'm waiting right now for Howard to actually tie into the webinar. So I'm going to go ahead and move forward with this, and hopefully Howard will tie in as soon as he can. So what we're going to be covering in the next hour is the overview of the envelope requirements for the commercial provisions of the code. We've split out the commercial into three distinct sections, one on the building envelope. Tomorrow will be on the mechanical requirements of the commercial provisions of the code. And then on Thursday will be the lighting requirements. And so it's easier to split the three out like this versus trying to do them all at once, because we can get them easier onto 1 hour segments versus trying to do everything at one time. So just a little bit of background about myself and our involvement in your code. Cadmus Group was contracted with the Hawaii State Energy Office to help update your current code to the 2015 International Energy Conservation Code. And during that process, we worked collaboratively with industry in Hawaii, your State Building Code Council, the Energy Subcommittee, to come up with good amendments to the energy code that were going to be Hawaii specific. The International Energy Conservation Code is a code really focused on the mainland type of construction, mainland type of climate zones, and it doesn't lend itself well typically to the Hawaii code.
Okay. And Eric, you're hearing me?
Yes, I am, Howard. Welcome.
Good. Humble apologies. I dialed in on the wrong station there.
So that's okay.
In mute. Yeah.
So just a little glitch. So not a problem.
Mm-hmm.
So anyway, Howard, I was just telling him kind of how our involvement was in the energy code as far as helping develop, working with you folks to help develop the code for the state of Hawaii, and making sure that the amendments that were put into place reflected your methods of construction and also your weather. So I'm going to turn that back over to you now, Howard, to move forward with this.
Okay, it gives me great pleasure. This is Howard Wigg, energy analyst with the state of Hawaii. I have been in this position for over 30 years and started the code development process back when the energy codes first became a reality, and have followed progress ever since. And my specialty has been, as Eric was indicating, to Hawaiianize the code to adapt the mainland code to Hawaii's unique conditions. And this applies especially to the envelope provisions. That's a bit about me. I think Eric maybe didn't introduce himself properly. He is a very, very tall presence at the national code level. These codes are developed by convening several hundred of us in a hotel ballroom and hashing out literally hundreds and hundreds of proposals. And the ones that make it to the top become the new code. And Eric is always there. I swear he participates in maybe 1 out of every 4 resolutions that comes up, because he is hired by many, many different entities to represent them on the energy code level. So I think we can go to the next slide, Eric.
Okay, let me just get that queued up here, Howard.
Okay.
Great. I'll go ahead and take this. So as we go through the presentation today, the way we're going to structure the webinar is that we'll present all the material first, and then we'll go ahead and answer questions following that. And the way we would like you to submit questions is to go ahead and email this to the email address on the slide, jolyn.green@cadmusgroup.com, and I'll keep this up for a minute so that you can go ahead and write this down. We will have an identical slide at the end of the presentation, so if you don't have it written down now, you can always do that once we get to the end, and we'll start answering questions. So go ahead and email in questions as they come up. We'll go ahead and answer all questions at the end of the webinar. So again, I'll give you just another few seconds here to write this down, and again, we will be bringing it up. The other thing we want to do,
and we do welcome questions also.
Absolutely,
so please send them in.
Yeah, we have about a half hour blocked off for the end of this webinar just to answer questions. So so go ahead and send in any and all questions that you may have about this. So the other thing is that you know a little bit about Howard and I, but we aren't sure of who you are as from a target audience standpoint. So what we want to do is take a poll and give you a minute or two to define yourself so that we have a better sense of who we're presenting to. And I'm going to go ahead and get this poll set up, and I'll launch it so that everyone can. The poll is now open. If you can go ahead and take a few minutes and define yourself so that we know who you are, that would be great. And I'll give you about a minute to do this, I think. So hopefully you know who you are, and if you don't fit into any one category here, then you fall underneath the other category, and that has, over the last two webinars, has been our largest category so far. So it looks like everything is pretty well stabilized here. I'm going to go ahead. I'll give you another 5 seconds, and I'll go ahead and close this, and I'll share the results so everyone can see who is on the phone. So, right, I'm now closing it, and now I'm going to go ahead and share the results with everyone. We have a great, a good mix today. Actually, we have a lot of architects, so welcome. That's great. This is definitely the presentation for you because it does focus on the building envelope. Building departments and plan review and inspectors, about what are we at, 15%, so a nice grouping there. Engineers, a good grouping. Some general contractors, which obviously this impacts your work. And then we have the other category, which Howard and I talked yesterday, is probably means that you're either a consultant, utility rep, you could be a manufacturer, product manufacturer, or product supplier, but that's kind of that's what would fall underneath the other category. So, with that, yeah, go ahead, Howard.
Well, Eric, my slide is not advancing. I'm still on Jolynn's email.
You'll still be on Jolynn's email until I
thought you were showing results. Okay.
No. So anyway, I should be able. I thought I shared this. Let's see if it. I think it did. It should have shared, but if it not, we can go through and I'll go ahead and hide this, and we will jump into.
The server connection was lost. I can't hear you.
Oh, Howard, the server connection was lost.
Ooh.
You might want to unmute somebody and ask them.
So let me. I'm going to go ahead and So Gail can't hear me. Okay, I'm going to go ahead and, I've just lost my server connection here, Howard.
To me or to everyone?
To the, no one can hear me on that end.
Ooh.
So what we may end up having to do is, we may end up having to have you present, and I will queue up the slide for you.
Oh, okay, because everyone, is there a way to go back and forth? When it's your turn, or?
No, because I've apparently can't, no one can hear me. I'm going to go ahead and click on, let me go ahead and see if I can get someone to, I'll pick this first person up here to unmute them. So I've just, Aaron Wallen, can Aaron Wallen hear me? I've just unmuted you. What's the matter? Oh, they can. Okay, great. Apparently, people can hear me, Howard. So I think we're
Oh,
good to go. So our
oh, okay.
yeah. So apologize for this technical glitch. It's the
Yeah.
broadcasting across the Pacific sometimes doesn't work well. So
So is everyone unmuted then?
everyone is now muted. So we're all set
Muted.
and ready to
Okay.
go, and so we should
Okay.
we should be good. So you're on the introduction slide now, Howard. Can you see that okay?
No, I'm still on the Jolyn slide.
Um,
It said it lost its server connection
Yeah. Oh, the message was lost server connection
to go to meeting webinar.
to go to meeting webinar.
so you have been blocked off.
I guess so. Let's see. No, I'm not getting a message like that.
I got it.
Oh, but Gail got it.
Jolene, are we still on? Do you know? Okay, so they're going to. Okay, so we're still on. We apologize for the what's the delay. I'm going to go ahead, Howard. If you can log off and log back on again,
Mm-hmm.
and we'll try to get you. So I think we Jolene just talked to Gail. So if you can get out of the webinar and then get back in, and
Okay.
I'll go ahead and proceed through, and you can jump in when you get back on.
Sounds good from here.
Great. Okay,
We'll
so
do that.
good.
Okay.
Okay, so let's go ahead and we've talked a little bit about the code. We've talked a little bit about what it covers, and what I want to do right now is actually get you into the structure of the code, because the code, one of the changes to the code is that it's now in two books. The IECC, it's almost two separate books combined into one book, with one section dealing with commercial provisions of the code and the other one dealing with the residential, but the chapters start with chapter 1, 2, 3, 4, and 5, and 6 for each of the residential and the commercial provisions of the code. So we always start off with scope and application, and this kind of lays the groundwork for the code. It will tell you what has to comply and what doesn't have to comply, what's exempt. There's a section on definitions, and so if you need to know what's happening, what's a term means, and terms and definitions, just like with all codes, are italicized. So you'll be able to tell if the word's italicized in the code, you can go to chapter 2 in the definition section. General requirements, this is where your climate zones are, and for Hawaii, you're now on the commercial side, climate zone 1A, but there's also now a tropical zone climate that applies to you. Even though there's no provisions for tropical zone, you are considered a tropical zone type of climate, but you're also climate zone 1A. Where we start to diverge now is where from chapter 4, you have chapter 4 commercial, and we'll focus on that since we're talking about the commercial provisions of the code. So chapter 4, commercial energy efficiency, and this is broken up into subsections. You have the building envelope, you have the HVAC and mechanical section, you have service water heating, you have lighting, and electrical, and then there's other things mixed in with that. For example, the 2015 code now covers refrigeration rooms, and refrigeration systems. It also covers people movers, which would either vertical or horizontal people movers. So it'll be escalators and elevators. There's provisions in there. There's transformer requirements. So there's several requirements that are actually in the chapter 4, the commercial provisions of the code, that we're not going to get into today. Then there's something called the options packages, and this is something that you have to comply with in addition to the prescriptive requirements, and we will talk about that. Chapter 5 is for existing buildings, and this is a brand new chapter. You didn't have it in the 2006 version of the Hawaii Energy Code, but it is now in your 2015 version. So existing buildings deal with what do you do with an addition, alteration, renovation, or repair for an existing building. And it provides some guidelines and a roadmap on what has to be complied with in order to get compliance with those that particular type of building. And then chapter 6 is reference standards. So there's a lot of standards referenced in the IECC. In chapter 6, we'll list them all. These are going to either be ANSI standards or ISO standards, or there's multiple standards that are actually listed throughout the code. And again, chapter 6 has a listing of all of those particular standards. So let's keep on going to the next slide. As part of the work that we did for the state of Hawaii, we went ahead and projected energy savings, did an energy saving forecast for what happens if the code is adopted, and we start getting construction built to that code as of 2016. And we did an energy savings forecast for a 20-year forecast, because that's typically the way forecasts are done, is for about 20-year period of time. And what we did on this is we actually looked at cumulative energy savings. We assume that a building built in 2016, for example, for this year, you're going to continue to get that energy savings all the way through a 20-year period of time. And as Howard would like to say, that energy codes are the gift that keeps on giving, because you get the same, theoretically, you get the same savings in 2016 for that building as you get in 2017, 2018. So every year you continue to get the same amount of energy savings. And you can add that up and you actually accumulate that amount of energy savings you get. So what we've done is a cumulative energy savings calculation, and we estimated the first year energy savings. Let's assume that a building was built in 2016 is about 11 gigawatts, and we've, it's always a question of, well, how much is a gigawatt, or how much is a megawatt, or how much is a kilowatt? What's that mean? But a gigawatt, we tried to break this down to say, okay, a gigawatt is basically power for approximately 200,000 homes for 1 year. So it's a significant amount of energy if, based on the construction start data we could have, if you assume that all the buildings were built underneath the code, looking at construction starts, you can see you can actually accumulate a significant amount of energy savings as you go through. So total for 2036, which would be a 20-year time period, would be 3,386 megawatt hours per year. So actually, that should be gigawatt hours per year. This is the MWH should be for gigawatt hours. So it's a significant amount of energy savings for commercial. When you combine that with residential, you're looking at about 4,700 gigawatt hours per year for a 20-year period. And if you calculate that and say, okay, 200,000 homes per year for 1 gigawatt, that's a significant amount of energy savings. And with energy savings also comes cost savings from a utility standpoint too. And obviously, your utility rates are significantly higher. We're here in the Boise, Idaho market. We're paying about 6 cents a kilowatt hour. So we're finding this commercial code to be cost effective here, and in your climate and with your utility rates there, the savings is significantly greater. So this is a huge savings amount. So what we're going to get into now is the actual provisions of the code, and we'll get into the kind of section R401 is the general provisions, and it's basically the provision in the commercial section that says what is governed underneath the commercial provisions of the code. And a commercial building, we should probably define that too, is essentially everything that's not residential, which is that's the way the code is defined. So we're looking at office, retail, we're looking at warehouse, school. We're also looking at apartment buildings 4 stories and above. So a lot of the apartments being built in Honolulu, for example, are not residential. They're actually by code commercial buildings. So there's a lot that actually fall underneath the commercial provision. And again, anything that doesn't fall underneath commercial, which is going to be 1 and 2 story residential, multifamily 3-story less, those are all covered underneath the residential provisions of the energy code. So this is how this is structured right now. So when we start looking at the commercial provisions of the code, let's go ahead. Let's kind of take a look at what your options are for complying with the envelope requirements in the code. You can always comply with ASHRAE 90.1 2013. And if you comply with the building envelope with 90.1 2013, you comply with mechanical, lighting, service water heating, and everything else. So the way the code is structured is once you pick your code, you have to comply with that in its entirety. We're talking about the IECC right now. So we also have prescriptive requirements that we're going to be covering over the next while for the building envelope. And this will be minimum insulation values. It'll be glazing requirements. It will be air sealing requirements. So there's a whole set of prescriptive requirements for the envelope that we'll talk about. If you can't comply prescriptively, then you also have an option of the performance requirements of the code. And the performance approach is using computer simulation to actually model the energy use of the entire building. and demonstrate that that building in its entirety complies with the energy code. And this allows you to do trade-offs with equipment efficiency, glazing area, glazing percentage, insulation levels, lighting, lower lighting power densities, things like that. But it's a truly performance-based approach that predicts the cost for you to operate your building on a 1 year period of time. Typically, this is not done. In most cases, probably, if I had to estimate, about maybe about this might represent somewhere between 5 to 10% of the total compliance done in the U.S. is done based on the performance approach, and normally it's done for programs that are what we consider above code or stretch programs, going above and beyond what the current energy code actually requires. But it is an option available to you. Going to be overkill for a lot of buildings, but you may want to go ahead and use that. So let's go ahead and jump into the building envelope requirements. And first, we're going to focus on the insulation requirements of the code. And really, the structure of this code is not a lot different than what we have in the 2006 Energy Conservation Code. You have two different categories. You have, and this is probably the biggest difference, you have on the climate, you've got your building assemblies down the left-hand column of the table. Then you have something called all other, and this is all other commercial occupancies. And then Group R. So Group R is going to be high-rise residential. This is 4-story and above residential occupancies. The all other is actually, this would be retail, wholesale, warehouse, commercial, any other type of commercial building falls underneath the all other. And in some climate zones, and actually as I'm looking through this table, there is a difference between the all other and Group R type of requirements, because typically, people occupy commercial buildings during the day, whereas on the residential side, most people occupy those buildings on the kind of in the off hours. Whenever you're not at work, you're at home, and so the requirements are slightly different to take account for the different when the different loads are in those particular buildings. So the first requirement we have this is divided into sections. You have your roof assembly, wall assembly, below grade walls, floors, and slab on grade. And you'll see there's a lot of NRs on here. So that means not required, because from your tropical climate, it doesn't make sense to put in to insulate some of these assemblies because there's no energy benefit. But when you
and Eric, I'm back on the line.
Oh, good. Okay, Howard. We're just going into the prescriptive requirements, and I think these are my slides. So yours are.
And I've got printed out slides, so you just need to guide me through here.
Okay, good. So we're just talking about the insulation requirements, and I'll just keep going and turn it over to you when your slides come up. So from a roof assembly standpoint, you have insulation entirely above the roof deck. So this is a built-up roof system. It's R20 continuous insulation. The CI on that means continuous. Metal buildings, and this is for all other, R25 for a Group R. Metal buildings, you have an R19 plus an R11 liner system. So a metal building would be a metal building like a warehouse building, or we call them butler buildings. It's essentially all steel frame, all metal construction, and your insulation is going to typically go underneath the roof assembly. So you install the R19 insulation. You actually drape that over the top of the purlins, and then you put the R11 insulation between the purlins, and the liner system is almost a vapor retarder type of system that supports everything. And then if you have an attic assembly or something that doesn't fall underneath the roof deck or the metal building, then you have an R38 ceiling installation. That's typically installed between framing members. For walls, you have a few different options on here, and we have provided a trade-off for some of these. Mass wall is going to be a CMU block or tilt-up concrete type of construction, and this shows that you're required to have an R5.7 continuous insulation. There are trade-offs allowed in the code. Typically, if you insulate the core of a mass wall, you don't have to put on continuous insulation. The CI again means foam board insulation either on the inside or the outside of that mass wall system. If you're using framing for wood framing or metal framing, it's an R13 installed between the stud cavities, either metal or wood, plus foam board insulation on the outside. And again, we do have a prescriptive trade-off that you can use on this to actually eliminate the foam board insulation. And then So that would be for metal or for wood, and then also wood framed. You can do basically what was equivalent to a 2x6 stud wall with R20, or an equivalent for metal framing of an R20, or go with an R13 plus the R3.8 continuous. So it's essentially you pick your framing type, pick your construction type, and then go ahead and apply the insulation levels. And the next slide will actually show you how to trade off some of the wall insulation, because in Hawaii, cavity insulation works really well, but really you can get rid of the exterior foam board insulation on most without impacting the energy performance of the building. And we'll show you how to do that. So below grade walls, this is if you actually have your building dug into the side of a hill, and with the below grade or almost a basement type of construction, there's no insulation requirement there. And you can see the NR for floors, there's no insulation requirements there because it really doesn't make sense in your climate to do that. Same with slab on grade, NR on that one. And then heated slabs, if for some reason you want to heat your slab, and I'm trying to think of a reason why you'd want to do that, you do have to insulate your slab edge, just because your slab becomes your heating source. But again, this is you're probably never going to see this. And then last but not least, non-swinging doors. They are required to be insulated to an R4.75. So you can have, for non-swinging doors, this would be large roll-up doors. So think of a car dealership or with a lot of service bays, for example, and you have quite a bit of a roll-up door on there, and that's a significant energy use. It's a significant solar gain coming into that door. So you are required to insulate those to at least an R4.75. So I've talked a little bit about the trade-offs, and one of the things when we did our analysis for the code, and we did quite a few Energy Plus runs for Hawaii, primarily because we wanted to make sure that the types of trade-offs and things like that made sense, that there was going to be energy savings, and from an energy equivalency standpoint, it all works. So what we found is that if you have a framed wall and you insulate the between studs, and you actually put some kind of a reflective reflective covering over that framed wall, it'll perform just as well as a wall with foam board insulation on the outside.
I can tell this story.
Sure.
Eric, in case you'd like to give your voice a rest there. You've done a yeoman's job of plowing through until I finally got through by voice. This is Howard Wigg again, and background to this trade-off is the fact it stems from the residential side, where we're very, very unusual in that about 75% of all new single-family homes built on Oahu are metal frame. On the mainland, that percentage is much, 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 much lower. So when a new code came out that required R5 external insulation for steel-framed walls, and it would seem to make sense because steel conducts heat 36 times as efficiently as does wood. So you need to break that contact between the solar radiation and the steel frames. It required R5 exterior insulation, and this came to the attention of the National Steel Framing Alliance. And even though they're headquartered back east, they flew the president and the chief researcher out here to meet with us and pointed out that for a single-family residence, adding that exterior insulation would add $8,000 to the cost of a home and would save only 484 kWh a year, because we have such a benign climate. And even back then, when a kWh cost about 35 cents, you still were saving only about $142 a year. You look at the $8,000 initial cost, $142 a year savings, and you come out with a payback of something like 45 years. Doesn't make a whole lot of sense. So we asked Eric to set about looking for alternatives, and we came up with reflective walls or overhangs. And the idea behind reflectance, in this case it's 0.64, is that 64% of the solar radiant heat that strikes a wall is reflected back. So you're only getting, what is that, 36% of the heat transferring through. That is a substantial amount. And then the other alternative is a 0.3 projection factor. If you had a 10-foot high wall, your projection factor would have to go out to 3 feet. And that works remarkably well too in Hawaii because our sun is so high. Think of all of the longer months that we go through. The sun is almost directly up in the sky, meaning that that projection factor is totally shading the wall for a large portion of the day. And then you look at the costs of these, and the cost is very, very little, especially for the reflective wall. And if you're going to do a projection factor anyway, which many buildings have on their lower floors, that makes great economic sense there. So that is the story behind these alternatives for the walls. And then once we had it for single family steel frame, the committee that I chair said, why not extend that courtesy to wood frame, and then why not extend it to commercial? So that is the story behind this particular amendment here. So we can go to the next slide.
Actually, Howard, I want to add one thing on here if I could. So, and actually, I think this was an amendment that you were going to propose for a county amendment to right now that we've only exempted frame walls, and we were going to add mass walls on here too. If I remember right.
That's right. Yes. Yep.
So that will be a county amendment that Howard will go ahead and submit. So.
And did you explain the county amendment business?
I did not. I did not because that was I thought I'd let you explain. So.
Yeah. Okay. Well, this is a good chance to jump in a few slides back. The code adoption process in Hawaii works as follows. There is a Hawaii Building Code Council that meets once a month, and the building division managers from the neighbor islands come here to Honolulu, and we all sit around a table. And the idea of the council is to make all codes statewide uniform. A lot of you are probably aware that traditionally the codes county to county have been a bit of a hodgepodge, and that makes it very difficult for architects and engineers and other designers to figure out what code belongs where. And another purpose of the council was to hopefully keep up with the very rapid national code changes that are going on. We're supposed to change codes every 3 years because technology is improving so rapidly that we want to keep up with that technology. So that step one is for the council to agree on certain amendments for Hawaii, and then the process goes through two paths. The state government path, which is called the administrative rule path, and we are proceeding on that with 2015 IECC, and the other is the county path, where according to the law that created the council, as soon as the council approves a set of amendments, the counties are free to take that ball and run with it and just put it through their own procedures. And that procedure would be the building division manager goes to his boss, usually the head of public works, who says, yes, this sounds like a good idea. He takes it to the mayor. The mayor says, yes, this sounds like a good idea. Then it goes to the council, the county council, and it goes through 3 hearings. And if at the end of 3 hearings it passes, then it goes back to the mayor's desk, and since he introduced it, he would approve it. And there may or may not be a lead-in time. Sometimes the last sentence of the bill says, this act shall take effect X days after signing. And X can be either 0 days, in this case it would be immediately upon signing, or 30 days, or 60 days, just to give the building community a chance to get used to this new law. So that is the process for adoption. And I should also mention that we're hoping that the state process will be through by the end of this year, and that one or two of the counties will have adopted by the end of this year, feeling that adoption will take place next year in 2017. So there's a bit of background for you. So Eric, are we ready? Did I miss anything, or?
No, I think you got it all. Why don't we move to the next slide, and you can take this one.
Sure. Solar reflectance. This is a issue near and dear to my heart, because in the warmer climates, not just Hawaii, but on the mainland, climate zones 1, 2, 3, that encompasses the southern tier of states, and southern California, southern New Mexico, southern Texas, southern Arizona. And these are climates that are dominated, what are called cooling dominated, where the air conditioner is on a heck of a lot longer than is the heater. And of course, here in Hawaii, we don't use the heater at all. So in that case, a reflective roof makes all kinds of sense, because for one thing, your sun is higher, and if the radiant heat strikes a reflective surface and bounces back up, it never begins to penetrate the interior of the building through the insulation layers. And we've done studies here in Hawaii where on a hot day, you can take a very dark roof, usually with a rough surface, and you will attain a temperature of 178 degrees. You coat that same roof with a highly reflective white coat, and the temperature drops to about 105 degrees. That is a drop of over 70 degrees. Now think of the implications for that. Your delta T between interior and exterior drops from about 100 degrees down to perhaps 30 degrees. A lot easier to keep 30 degrees of delta T out of the interior. That's a justification for reflective roofs. And so we in Hawaii were the pioneers in requiring reflective roofs, or offering it as an option. And we took it to the national level, and now it is true for climate zones 1, 2, 3, which I described earlier. So this is now an official requirement, regardless of what you're doing with your insulation. The exception being if you put PV panels on your roof, or a green roof where you're growing something, or you shelter the roof either all the time or most of the time from the radiant heat, you do not need to have a reflective surface. But those are the only exceptions to that rule. And keep in mind that this applies to white roofs, or flat roofs, I should say, low slope, because when you get to steep slope roofs in residential areas, people could see the white roof and object to it. So this applies just to low slope commercial roofs. And that is the story behind requiring reflective roofs. Just incredibly cost effective in terms of keeping the buildings cool and the air conditioning load down. That does it for me, Art.
Okay. And you have this slide too, Howard, unless you want me to take it. Yes.
Fenestration factor. Yeah, we had a lot of debate in talking about, at the national level, talking about SHGC, solar heat gain coefficient. And again, that is a measurement of the radiant heat striking the exterior of a window and measuring how much of that heat gets through to the interior versus how much is reflected. Your standard single pane glass has an SHGC of something like 0.85, meaning 85% of the heat penetrates right into the interior. The new code calls for an SHGC of 0.25, meaning only 25% of the heat gets through. And the technology that allows this is quite thoroughly incredible. You still have a clear view to the outside. And I won't try to describe how that is achieved. It's called a spectrally selective window technology. And at first, when we first pushed this through, the builders, contractors were concerned about high costs. But the wonders of mass production, the builders on the Ever Plains, again, just giving a residential example, tell me that they can bring in 0.25 glazing for a lot cheaper than they can bring in single pane glazing, simply because this is an example of how the codes have caused market transformation. The window manufacturing technology has changed entirely in this direction. So that's not all, though. We, especially in the warmer climate zones, really benefit from shading. I have personally taken a temperature of a wall that's getting direct sun, and it comes in at about 140 degrees. Then I measure a shaded area right next to it, same surface, goes down to 95 or 100 degrees, a 40-degree drop just from shading. Therefore, we have awarded shaded windows where you have if you have a projection factor of 0.2 or less, you must go to the 0.25, and there's an exception for your north-facing windows. They can go up to 0.33. Why is that? Because you don't get direct solar radiation. Then if you have a projection factor of 0.2 to 0.5, your required SHGC goes down to 0.30. And if you have a projection factor of 0.5 or greater, then you have a lesser requirement for your windows. And this would apply in Hawaii to the bottom floor of retail. Very often in a high-rise, you have the first floor being retail shops, and then living units or commercial spaces above that. And the retail shops are very often thoroughly shaded, which makes sense. The consumers can be out there shaded from the sun or from the rain. And very often those projection factors are greater than 0.5. So you can pretty well do anything you want with there. So that takes care of that for me, Eric.
Okay, great. Let's move to the next slide, and I'll jump in here, and we'll talk about one of the requirements and the prescriptive requirements is a maximum amount of glass area on the wall. And I believe the 2006 code right now is at 40% window wall ratio. So if you add up all of your glass and add up all of your above grade wall area, you divide your total glass area by your total above grade wall area, and you come up with a percentage, and we call that the window to wall ratio. So in the 2015 code, this actually dropped to a maximum of 30%, down from 40%. The reason being is that this was an increase in energy efficiency on the buildings. The most glass you can get prescriptively is 40%, but if you want 40% glass, then you have to do something to offset the additional energy use that you're going to get from more windows. Now, if you want an all-glass building, you're not going to be able to get it prescriptively. You're going to have to go to the performance approach that we talked about at the very beginning of the session. So there is a way of trading off, trading that off, but for an all-glass building, you definitely want to use trade-offs with equipment efficiency in the building or better lighting systems or something like that. So again, this is just one path through the code. That's prescriptive, and it may not work for you, but if you can make it work, that's great. So 40% or 30% is the maximum without anything special on the building. 40% you can have, and we'll go to the next slide, but you're going to have to put in daylighting controls in front of all your vertical glass and underneath all of your skylights. These are automatic daylighting controls, so daylight responsive controls. You also have to have a certain percentage of your floor area in daylit zone. because again, this is offsetting the energy, increased energy use of that additional glass. So for a low-rise building, 2 stories or less, you have to have no less than 50% of the net floor area in a daylight zone. Again, this can be there under a skylight or next to vertical glazing. As you go up, taller buildings, 3 stories or more, only 25%. 25% of the floor area has to be in daylight zone, and this is to recognize the fact that it's harder to get daylight zone into taller buildings than it is shorter buildings, because you don't have roof area and things like that to put in skylights. Again, you are required to put in automatic controls on all of underneath all your daylight zones or in your daylight zones, and you also have to make sure you have enough visible light transmittance through the glass so if you have windows there, you want to make sure you have enough usable light coming in. So their code basically says that your visible light transmittance has to be 1.1 times the solar heat gain coefficient. So Howard talked about a solar heat gain coefficient, a minimum requirement of about 0.25. So multiply 1.1 and you're at a visible light transmittance of what about 0.28 or something like that. So this makes sure the VT means visible transmittance. You have enough visible light coming in to be able to see when the lights are either dimmed or turned off in that space. So again, this is up to 40% of the of your a 40% window wall ratio building. So between 30 and 40, you need these controls. The next thing I want to talk briefly. Oh, go ahead.
Oh, Eric, let me jump in here. A lot of people, as you're discussing this area, are probably thinking Kaka'ako, Kaka'ako. Kaka'ako is a neighborhood of Honolulu between downtown and Waikiki. It used to be a light industrial area, and now it has become a high-rise, emphasis on luxury high-rise area. And they have gone up and are going up very, very, very rapidly. And virtually all of them look to be 100% glass facade. Of course, we know you can't be 100% glass facade because something has to hold the building up, but that's what they look like. And they have snuck in under the 2006 code rather than this much more stringent 2015 code. And Lord knows how they're keeping those buildings cool, because you have the direct sun, and this is in a sunny area of Honolulu also. So they must be taking all kinds of measures to keep the heat out. But had they had to conform to this code, they probably would have designed very differently. And with regard to visible light transmittance, one of these high rises comes in below the requirement and had a lot of reflectivity, and there was for a while a threat that they would have to take out all the windows and replace them, which of course would be a multi gazillion dollar prospect. But this has been a significant issue for Hawaii, and the ball game will change once this code is adopted. So that's that.
Okay, great. Okay, so we'll talk a little bit about skylights now. And right now you're limited prescriptively to 3% of your roof area in skylight. If you want up to 5%, you can have that, but you have to install automatic daylighting controls under in the daylit zones formed by the skylight. So kind of the theme behind the 2015 code is really integrating daylighting into commercial buildings, just so you can basically offset your internal loads by using visible daylight from the outside. And there's a very good energy savings in there. Now, there are going to be instances where you're actually going to be required to have skylights in your roof system. Right now, if you look at the slide, you have in certain types of enclosed spaces greater than 25,000 or 2,500 square feet directly under a roof, not less than 75% of the ceiling area, with a ceiling height greater than 15 feet. So if I have a large space that's greater than 2,500 square feet, and my 75% of my ceiling area has a ceiling height of greater than 15 feet. So think of a high school gymnasium, a warehouse. Those are probably two of the occupancies that come to mind. You need to make sure that you have enough skylights so that half the floor area is in daylight zone. The goal is to be able to do natural lighting in these spaces. We're already seeing large box stores, big box stores are already doing this, and they're seeing the benefit on that. Actually, there's been studies done that show that one of the retailers showed that they're installing skylights because they actually sell more product underneath natural light than they do fluorescent light. So there's an advantage that way. So in certain cases, certain types of buildings, again, you will have to have skylights. They'll require you to put them in just to make sure that you have enough daylight zone underneath that to naturally light the building. So Howard, you have the next slide.
Well, let me comment on the skylighting slide. Indeed, to my knowledge, I believe all of the big box stores are now automatically incorporating skylights. Again, think of the thousands and thousands of square feet that don't have to be artificially lit during the day. That is a huge, huge savings. And then in terms of sales, what we have found is that regardless of how good your artificial light is, it cannot exactly emulate daylight. And we as a species were in daylight or dark for the huge, huge majority of our ancestry. Homo sapiens have been around for over 200,000 years, and we only started spending a lot of time indoors after Thomas Edison invented the light bulb and machinery came in to take care of agriculture. So we still have it in our genetic disposition to prefer daylight. So when we see a daylit item in a big box store, say, we are more inclined to think it's familiar and to purchase it. So those clever big box guys have figured that one out. Now let me jump into the next slide. Area weighted SHGC. Very interesting story in back of this. When the first code requirements came out for high performance glass, we got some very concerned vendors coming to us. And these are the companies that go into residences and retrofit their window systems. And they have warehouses full of single pane glass. So they asked us, do you want to put us out of business by requiring high performance glass? And no, we didn't. So we worked with them and found that in Hawaii's benign climate, you can achieve the same level of fenestration performance of not allowing the sun's heat in if you did certain things. Number one, and again, this is starting with single pane glass. So number one, we exempted the north face of any, in this case, it was a residence, and now we transferred that to buildings. Why exempt? Because when you don't have direct solar light, all you have is the ambient temperature compared to the interior temperature. And in Hawaii, very often, that delta T, that difference, is as little as 10 degrees, 85 outside, 75 inside. Even a single pane of glass will do a good job of shielding you from that temperature difference. Then we went into a lot of shading, and the shaded glass was exempt, and we still couldn't get down to equivalent to 0.25, and it was one of the people sitting at our table in the council. It was an Australian, and he said Australia has a SHGC rating for screens. So I contacted the NFRC, the National Fenestration Rating Council, who puts these numbers on, and said, can you look at what Australia's doing? They did, they talked, and now screens are rated in America for SHGC. So if you have your screens plus all these other measures, you can achieve, with careful design, you can achieve a code compliance just with single pane glass. So that's the story behind that. You have to, there's a whole table that guides you through and allows you to plug in numbers so you can revise those numbers until you comply. So that's that story, Eric.
Great, thank you, Howard. Okay, so we've talked about installation requirements, we've talked about glazing requirements, and in some cases where you're actually going to have to install skylights. Now we want to shift the emphasis of this discussion into what other things you need to comply with for the building envelope. And one of the big elements right now that they're seeing fairly good energy savings is actually making sure your building is sealed up as best possible. Right now, we bring ventilation air into the building, and most commercial buildings through the mechanical system. And there's really no need to have holes and leaks and things like that into your commercial building unless your commercial building is actually designed for something like that. And Howard and I, we did training last November, and we're in some resort areas, and noticed there was a lot of natural ventilation being used in the resorts through lobbies and things like that with vent openings in the walls, and we've been kind of looking at that, trying to figure out how the code would apply to that. But for a typical commercial building where you're just bringing in standard air conditioning and the building is fairly sealed up, then you're going to want to have to make sure that you have a continuous air barrier integrated into the design of the building. And all this is making sure that the 2006 code had language that basically said seal up the building envelope. This is actually going to require you to meet one of three elements of the building envelope, or one of the three ways of complying with the code. The first way is actually installing the right materials and making sure you're sealing between those materials to reduce air leakage. The next one is actually you can install assemblies. So an assembly would be made up of materials and again seal between the assemblies. And the third option would be you can actually do an air leakage test using a blower door to see if the building envelope came in less than the maximum air leakage set up for that particular building. So the first option are materials, and if you look at this list of materials, you see typical construction materials, and the goal is to assemble these in your building envelope and seal between the materials to form a continuous air barrier. And the continuous air barrier is going to be in the assembly that surrounds the area you're cooling. So it's your roof assembly, your wall assembly, and your floor assembly. So that would be where you'd want your continuous air barrier. So these you can install kind of the pre-improved materials, and you've got sheetrock, plywood, you have different types of foam products. All of these actually reduce the amount of air leakage through the building envelope, and then you just have to seal between the materials to make sure that they're going to stay connected essentially, and you can reduce the amount of air movement through those materials. So materials are one way of doing it. The next way would be assemblies, and an assembly might be a CMU block wall, for example. A CMU block wall in this case with either a block filler or two applications of paint or sealer coating. If you look at the upper left-hand square, so CMU block automatically qualifies as an assembly. So our masonry walls constructed of clay shale masonry units with a nominal width of 4 inches or more. So these are assemblies that actually comply with the code. So automatically, without having you to show any kind of testing to show that your assembly complies. Last but not least is the air barrier testing, and this is showing a rather large building. We've got four blower doors set up on here. You might want to use this for a smaller building, maybe like a 5,000-6,000 square foot type of building that's actually constructed more like residential construction, and going ahead and testing that using a blower door. That's an option. You have to meet a leakage rate of 0.4 CFM per square foot of building assembly in order to comply with this. So again, all we're doing is making sure that the building shell is sealed up. We're reducing leaks and things like that in the building. We're already bringing in ventilation air from the outside into those spaces, so we don't really have to worry about stale air and that type of thing because we're already ventilating. What this does, though, is it actually reduces the load on the air conditioner because we're not bringing in air from the outside and having to condition that air through leaks and cracks and things in the building envelope. So it actually reduces the load on the mechanical system, and so you can actually, in a way, almost downsize your mechanical system because you don't have to account for infiltration loads as much as a typical building. So with that, I'm going to keep on going in the interest of time. Actually, I guess that's my last building envelope slide, Howard. So do you want to talk about the additional efficiency package options and And then,
Absolutely, absolutely. And I would point out that the last slide, building a very tight building can result in decreasing the size of your AC system, which can result in decreased fan energy consumption and even decrease in ducting. You spend money on the envelope, you save money on the HVAC system. So getting to additional package options, when we created the 2015 code, we wanted to achieve certain savings, and the measures described above did a certain amount of that, but we wanted more savings, and we know that builders, designers, architects, they like options. I've heard it time and again. Don't tell us how to build a building, just tell us what you want. So in this case, the designer is given an option of one more efficiency feature. And as you see, one efficiency feature would be higher HVAC performance. This is measured in SEER, Seasonal Energy Efficiency Ratio. And the building code is always a minimum, and there are much more efficient HVAC packages out there. I know on the residential level, it's a very dramatic instance. The minimum C is 14, or SEER is 14 now. There is a package out there available in Hawaii with a 32 SEER. And my air conditioning vendor friends tell me that 21 SEER is becoming increasingly popular. So that's a fairly easy one to comply with. Even easier would be decreased lighting power density. LED lamps are improving in performance, both in life, and color constancy, and in efficacy so rapidly that the existing lighting power densities are pretty well obsolete. You can go over this very, very easily. My electrical engineering friends tell me that. Next one, enhanced lighting controls. That would be quite a bit more expensive, quite a bit more complex. So I think people will pass on that. But look at the next one, on-site renewable energy. Think photovoltaics. If Hawaiian Electric can figure out how to balance the load, the considerable PV load they have out there, with their needs, they can start permitting PVs again, and this would be another easy option. And can keep in mind that when you put PVs up on your roof, you are shading that portion of the roof, reducing your heat gain through the roof, so you can benefit from that also. Dedicated outdoor air probably doesn't work too well in Hawaii because of our high humidity level. But then the final one, high efficiency SWH, solar water heating. We have over 100,000 units up in Hawaii, in our little state, and especially, say, for apartment buildings where you have a high need for water heating and a nice flat big roof. You can put very easily put solar water heating up there, and then block off a couple of parking stalls and have great big tanks to feed everybody. That works very, very effectively also. So all you need to do is pick one of those to comply, and that's in addition to all of the requirements that we've gone through before. That's all for me, Eric.
great. Actually, I just wanted to add a couple of things on the slide, Howard. And you had talked about the reduced lighting power density, and that is an option. Howard and I participated in the development of the 2018 International Energy Conservation Code, and one of the requirements that they're trying to get in is to reduce the base case lighting power density by somewhere between 10 to 15% over what we currently have, essentially to account for the huge number of LEDs that are being used in current design. So we're already seeing the numbers drop significantly, and that's based on what we're seeing right now on states that have adopted it seems like the reduced lighting power density is kind of the option of choice for these requirements, just because it's a fairly easy number to hit. The other thing I want to correct you a little bit, Howard, on the high. The SWH is actually service water heating. So this is not solar water.
Okay.
Solar water
Oh.
heating would actually go underneath the on-site renewable energy, so it still allows you to use solar thermal there. But this was the service water heating is essentially for, and it's limited to certain building types that actually have very high water heating load. So it's putting in a more efficient water heating, a conventional water heating system. So, but certainly what you were talking about, Howard, falls nicely into the on-site renewable energy, because you can either be PV or solar thermal. So anyway, and we actually in the 2018 code, this list expanded. We added another 2 on here. One is for building envelope, and I can't remember what the other one was, but there'll be 2 additional. Air leakage. Actually, you can get a tighter building. So we actually, in the 2018 version, there'll be 2 more options for this particular one. So anyway, why don't we go to that's it for the presentation. And now what we'd like to do is answer your questions. And so if you have questions, please feel free to email them to jolynn.green@cadmusgroup.com. And we already have 5 questions, Howard, to start with.
Oh, good. We love questions. We love questions.
Yeah. So, and we actually have, we have time. So please feel free to email more in if things come to mind. And then, the next slide, when we get into it, we'll tell you if you have any additional questions, Howard's contact information. So we'll get to that. But first, let's look at the questions that have come in, Howard. The first one says, and you were. This is when we were having technical difficulties, and you hadn't been able to get in on the webinar yet. So I'll take this first one.
Okay.
You mentioned the envelope compliance can be achieved following ASHRAE 90.1 2013. The presentation states 90.10, which is true 2013 on slide 10. And the zeros should not be there. This is ASHRAE standard 90.1 2013. So there was a misprint on that slide, and I need to correct that. So it's 90.1 2013. So that's the correct ASHRAE standard to use if you don't want to use the IECC for the building envelope. The next question is on heated slab. We talked about heated slab for the opaque envelope, and I had said that if you have a heated slab, you have to have slab edge insulation. That's the only time you need slab edge. And the question basically is, does heated slab mean radiant flooring? Yes, actually it would be radiant coils within your slab. Or actually if you have, if you wanted to heat your building and you ran ductwork in or under the slab, that still counts too. So there are there's actually a definition for heated slab in the code, but it's definitely from a radiant floor is probably going to be the most common, and so that's exactly what I'm talking about, radiant flooring.
That is the last question I would expect in Hawaii, but I guess it's done somewhere.
Yeah. So Howard, I'm going to throw a question out to you here. We were talking about PV panels, and you had mentioned the exception using PV panels for a cool roof system. And the question is, does the roof need to be 100% covered, or is there a minimum percent coverage to qualify for that exception? So you had said that if you have PV panels on a roof, then you're exempted from the cool roof requirement.
Okay, that's an easy one. The exempt portion of the roof is that portion which is under the PV panels, which is fully shaded. And if there are other items on the roof that fully shade, meaning shaded all day long or almost all day long, those portions of the roof are likewise exempted.
Okay.
But generally, I should add that the fire department does not want us putting PV panels all the way to the edge of the roof. They want 3 feet around the perimeter so that they can get up on the ladders and get their feet onto solid ground. They don't want to be walking on live solar panels while they're trying to put out a fire. So
Understand. Okay, I was going to say understandable, Howard. So yeah.
Mhm. Yeah, at the code council, I sit right next to the deputy fire chief, so he made that very clear to us. And so that portion, only the portions that are covered are exempt from the reflectance requirement.
Okay, and actually, the person that asked the question did make the comment that you must, this falls under line with what you said, that the new NFPA code does not allow for 100% coverage.
Hmm.
So that falls directly in line with what you were talking about. So Howard, I'm gonna throw another question out. We just got another few questions in, and
Sure.
this is going to be on jealousy windows. And this is an interesting one that I think you and I have talked about a little bit, but will there be a commercial option for air infiltration and jealousy windows?
Hmm. I didn't we include that in the commercial?
Not for
I
commercial only. Oh, we only actually included um, the increased allowance in air infiltration for tropical zone homes using jealousy windows. That's the only place that we've actually included that
hmm.
in the code. So, and I think this kind of goes hand in hand with our discussion when we were training about natural ventilation in commercial buildings and how that's handled in the
Hmm.
code. So anyway, I think this is something you're probably going to need to look into, right, to figure out how
Yeah,
this to.
yeah, yeah. As I was indicating before when I was describing the code adoption process, one path is the county path where the county councils consider they're free to amend the state code or the national code. And an argument could be made for allowing jealousy windows with their added air infiltration into commercial buildings because very often we have such beautiful weather that we don't need AC. And in those cases, we can just turn off the AC, open up the jealousy windows, and we're nice and comfortable and we're saving energy. And another factor here is that our high rises can have openable windows no more, I believe it's than 6 inches. And this is called the baby amendment, where a young child with a high rise in a high rise with an openable window crawled up on the windowsill, fell out, and died. And so there was an amendment permitting openings no more than 6 inches. Uh, in this case, jealousies would be the ideal solution for opening up high-rise, especially say living units, because your space between the jealousy windows is certainly less than 6 inches. So, to summarize, I would encourage this an amendment to this effect at the county level for
Okay.
commercial buildings. Yeah.
Great. Okay. I'm going to take a question here, and then I've got some more for you, Howard. Actually, the questions keep coming in, so this is great. It's
Mm-hmm.
a lot of great
Yeah,
questions
we
there.
asked and we got. Yeah.
Yes. So the question is, we talked about daylight zone, and the question in here is, what defines a daylight zone? And the daylight zone, first of all, there's two types of glazing or fenestration you can have in your building. Vertical fenestration, that's a window, and then horizontal fenestration, which is also called top lighting from a daylighting standpoint. So the daylight zone in front of my window is from the surface of the window 15 feet into the room or to the nearest floor to ceiling height partition, whichever is less. So 15 feet in or to the nearest floor to ceiling height partition, and then 2 feet on each side of the window. That defines my daylight zone in front of that window. Under a skylight, they've modified this a little bit. It's now you take the ceiling height and you multiply the ceiling height by 0.75, so you're basically 3/4 of the ceiling height, and then you add that distance to each dimension of your skylight and project that down onto the floor. And that becomes your daylight zone. So again, it's 0.75 times the ceiling height, and this is all defined in the code. That distance is added to each dimension of the skylight projected down to the floor, and all the lights in that daylit zone have to be controlled separately from the other general lighting. So again, you two different types, and also the code has got several diagrams on what you do with it. monitor lighting and things like that. So there are different configurations, obviously, of different window and skylights that you're going to see in commercial building, and the code does a pretty good job of providing those diagrams to show how to calculate out the daylight zone underneath those spaces. And I'm going to take one more question on here, Howard, that actually is seems to be a follow-up. What is the level of illumination required in the daylight zone? It's a great question, and it's really whatever lumens you need to do the task that you're trying to do in that zone. So if you have a work surface and you need 50 lumens for that work surface, then that's the level of illuminance you're trying to achieve, and you either achieve that through natural light coming into the space, or overhead lighting, for example, or task lighting. So you have a few different options, and so it really is going to be dependent on the illuminance you actually need to be able to perform the task for that particular space or on that work surface. And that's what you're going to be trying to figure out, how much daylight to come in, and how you're going to be setting up your controls on your lighting for that particular space.
And let me jump in to add to that. These light levels are determined by the IES, Illuminating Engineering Society, and the latest handbook, I'm looking at it now, is easily 4 to 4.5 inches thick. It is a big book. And one reason for that is that for each area in determining the lumen level, there are now 3 options. Number 1, for occupants, primary occupants, age 25 and below. Level 2, age 25 to 65. Level 3, age 65 and above. And the difference between level 1 and level 3 is about a 2-to-1 ratio. So that adds to the weight of the book. Generally, people will just choose the middle level as their illuminance.
Okay, great. Okay, Howard, I'm going to add. There's a multi-part question here that I'm going to put to you, because this is something you've been dealing with quite a bit. And the first part of the question is, what are some of the options, either specific products or manufacturers, that are available for coverings with a reflectance greater than 0.64?
Okay, I cannot mention any specific companies, but what I did in researching this was I went to various paint stores in Hawaii, and of course they offer both interior and exterior paint, and they have what are called paint wheels or paint blades, where for a given shade, let's say light blue, they will, or no, let's say blue, the one paint blade will have generally 7 different options, starting with dark blue and then going lighter until the lightest color is something like eggshell blue or even lighter. And generally the two lighter of those 7 options are either 0.64 or above, because you always want to be giving people options. So that was the method of determining. Oh, and then I talked to the paint companies themselves, and I said, "Is this a reasonable option?" So that is how we arrived at that 0.64 option, or 0.64 standard there. And what was the question again? I got.
So actually, I think you answered that one. What are some of the options that are available for coverings with that kind of a reflectance?
Let me illuminate that a bit. The major paint companies offer reflectance levels only of visible reflectance. That's what is recorded by our human eye. There are a couple of, or maybe 3 smaller paint companies that offer solar reflectance. And that is a more relevant number, because people will recall that the visible light spectrum is between about 380 nanometers on the violet side, going up to about 750 nanometers on the deep red side. And after 750 comes another spectrum called FIR, far, no, let's see, what is it? Near infrared, NIR, and that's from about 750 to 1200 nanometers, and that is where most of your radiant heat resides. So the best we could do was visible, but if you look at wall coatings, solar reflectance for wall coatings, you will see some companies that offer the solar reflectance, and I'm trying to work with the major paint manufacturers so that they too will offer solar reflectance.
Okay,
But
and how?
otherwise, they're pretty well all the same.
Okay, so is one of the follow-on question: are these reflective surfaces extremely glossy or shiny?
No, I mentioned the 7 different options. Say the number 6 option is not. It's light, but it is not glossy. It's not shiny. In this case, there's no correlation there. It can be a flat paint.
Okay, great. And from a cost standpoint, I mean, are the costs fairly comparable with the paints you looked at? Is there something
Yes,
that's okay?
yeah. I specifically asked that, and there is no cost difference between the darker colors and the lighter colors.
Okay, great, good. Okay, there's one question we have a few questions here, which is good. I'm going to answer one question, I think, and I might throw this one to you too, Howard. We had talked about the eliminating the continuous insulation requirement for mass walls if you install a reflective surface. Do you know, will that amendment be in the county amendments the package you're putting together?
Don't know. The county people have not informed me of that. Being a state person, I certainly cannot impose my will on them. I will encourage it, but I don't know if they're going to take me up on it. I don't know why they wouldn't, because the reflectivity of a mass wall would be equal to the reflectivity of any other type of wall.
Right, and really oh, go ahead, sorry.
Oh, it doesn't add cost. You're going to coat your mass wall with something anyway. Why not coat it with a reflective surface?
Right. And actually in your zone, based on the analysis we did, that CMU and concrete with a reflective surface or a shaded wall actually works quite well. From an energy standpoint, it works very well. So one question that I think you may have covered, but it's worth repeating because I'm sure it's on everyone's mind, is when will the IECC 2015 be put into effect in Hawaii?
Okay, that's a double part answer. There's 2 paths, the state government path, and that involves, I'm trying to count the steps, at least 8 or 9 different steps. And we are on step 5 right now, so we have 4 steps to go. I'm hoping that we will finalize this before the end of this year, and maybe well before the end of this year if all the parties involved move rapidly. And that's a hope, not a statement. The second path is the county path, and the county of Kauai is already moving forward with the energy code, so they may adopt it within the next few months. And then the other counties will follow either late this year or sometime in 2017. Not a definite answer, it's just how government works.
Okay, great, good. Okay, and there's an interesting question that someone's already looking to the future of the maybe the 2018 code. But the question is, as soon as we are aware of next code edition, so I guess that would be the 2018. Can we add a county amendment that allows the designers to refer to these allowances before the next code gets adopted, since it is in the intent of the IECC? So I think making sure that, if I'm reading the question correctly, making sure that the amendments that were made for the 2015 gets into the 2018. Is that feasible, Howard, or how would you?
We're talking about the Hawaii amendments.
Yes.
Yes. Yeah. Generally, unless we specifically exclude something, all of the existing Hawaii amendments will transfer to the next code.
Okay, great. And how does someone get involved in this code development process in Hawaii?
By emailing me, and when we wrap up here, you will get my email address.
Okay.
And asking me the question, and I will. It's probably specific, and I will give them a specific answer. And we love people to get involved. This is a democratic process.
Great. Good. So anyway, there are a couple of other questions that I think they're probably best answered via email, primarily because they're going to take a little bit of thought, a little bit of explanation to be able to answer those questions. But we'll get those answers to you fairly quickly. Howard, do you want to take us home here?
Yeah. Are we on the last slide?
We are on the last slide. Yes.
And is my email address on that howard.c.wig?
You have all of your information that someone needs to contact you.
Okay. One lesson we've learned through this is that the more carefully you design your envelope, the better job you'll do of keeping the heat out. Therefore, you can actually reduce your HVAC size and cost. So definitely keep that in mind. And then in terms of lighting efficiency, the lower your wattage of light, the less heat you're producing, the less you are affecting your HVAC system. So please keep that in mind. And even though we have still the 2006 code, there is no law against going above the code. Please do. We've done surveys, and the major architectural firms and engineering firms are going way, way above 2006. They're much closer to 2015. And the same applies to the production residential builders on the Ewa Plains. They're way, way, way above 2006. So please regard that as an antiquated code. Take advantage of the advanced technology, which in many cases adds no cost whatsoever, and you're delivering to your client a much, much better building. And that about does it for me.
Great. Thank you, Howard. And thank you, everyone, for attending. So that everyone's aware, we also have a webinar on the mechanical provisions of the 2015 IECC tomorrow. And on Thursday, we have a webinar covering the lighting provisions of the 2015 IECC. So please feel free to sign up for those if you haven't already done those, and attend those sessions.
And when these are all through, we will be putting all of these webinars up on the departmental website, Department of Business, Economic Development, and Tourism.
Great. All right. Thank you very much. And again, thank you for attending, and hopefully we will see you on the next two webinars. Thanks. Bye.
Aloha.